Hey kiddos, 22.1 Conditional Probability Geometry. Our essential question is, how do you calculate a conditional probability? Our shortest answer is basically we can calculate the conditional probability of P of A given B from a two-way frequency table, and using the formula of the probability of A given B equaling to the number of elements within set A intersection B divided by the number of elements in set B. Now you can also calculate the probability of A given B using the formula of the probability of P given, or P, the probability of A given B equaling the probability of the intersection of A and B um, divided by the probability of B. Now, real quick, something to note is that's basically the same, and I'll show you the two variants of how we write that. All right, so it's not just what's the probability of this event happening. Now it's like, okay, well, what's the probability of, like, for example, what's the probability of drawing a jack that happens to be red? So it's like, well, you have to consider, well, what's the probability of getting the jack, right? So that's like what, 4 out of 52? But then again, what's the probability of it being red? Well, probability of it being red is 2 out of 52. So how do we find the probability of those events occurring given that your jack has to be red? So that's where conditional kicks in. And again, the way you read this is the probability of A given B. Okay, that's what that little wall there is meant to represent. All right, here we go. All right, so again, finding conditional probabilities, the probability of event A occurs given that event B has already occurred is called conditional probability. So my example that I kind of mentioned is the jacks have to be red, uh, but you're drawing the probability for a jack, but it happens to be red. So red has to already have happened. All right, so this is coming back from a recent two-way frequency table from earlier on, I think in module 21. But it's a two-way frequency table showing medication, no medication, and headaches, no headaches, out of 100 people here. Now, we're going to go ahead and find, let's see, let event A be the event that a participant did not get a headache. Okay, so no headaches. Okay, so I'm looking at no headaches. For A, let B be the event that the participant took medicine. Okay, so that's very important to notice. Now, to the nearest percent, what is the probability that a participant who took medicine did not get a headache? So it's like we have to consider, given the situation, that we did not get a headache. Now, we have to figure out, well, how many people, how many participants took medicine? Because again, given that they did not get a headache. Well, medicine. Let's see who medicine. Um, let's see. Participants took the medicine. All right, I'm saying a total of 65 people. So we got 65 participants who took the medication. Now, of those 65 people, how many did not get headaches? Um, let's see. No headaches. 54. Okay, so 54 people did not get headaches. So the probability of A given B is pretty much this. We have 54 people who took their took their medication, so that's 65. 54 over 65, you get about 83%. Okay, so let's check out B. To the nearest percent, what is the probability participant who did not get a headache? Sorry, the H and E got kind of ran off there. Took the medicine. Ah, so how many participants did not get a headache? All right, so we got 76, right? All right, did not get a headache. But out of those, many took meds. So let's see, took medication. 54 people again. Yeah. So the probability of event B occurring given A would be written like this. We have 54 people out of the 76 total that did not get the reported headache. Round to the nearest. Okay, so plug that in the calculator, you get 71 percent. And then let's see, let's talk about C. So the numbers in element A. So again, event A is the participants who did not get a headache. So how many people did not get a headache? We got 76 people. Event B is the event that participants took meds. So how many people took medication? That was 65, right? Yeah. Now, how many are in A intersecting B? So they're in both events. That would be 54 from up here, right? So they took meds and they had no headache. So the intersection would be 54 people. Now, when we're expressing the probability of A given B or vice versa, we really have to be aware that, again, the probability of A given B is really going to be the number of elements that are in the intersection of A and B, or number of elements in the intersection, divided by the number of elements in uh, the given event. And the given event is the participants who took meds. So it's like we're really focused on the fact that they already took their medication. We're not focused on people who did not take their medicine. All right, so that's a big important part, right? So you're not thinking about those people down there, no meds, okay? Now, the probability of the event B happening given A is just going to be this. It's very similar. It's basically the number of elements within the intersection of A and event B. But instead of divided by the number of elements in B, it's just divided by the number of elements in A. So you can see how it just kind of flips the denominator. You're still using for the same numerator, here and here, but notice how these denominators they kind of flipped. All right, so that matters. All right, so let's go ahead and look at conditional probability again. This is one of the key things to definitely memorize and to be aware of. Okay, so it's probability of A given an already given event, B. All right, so example one. Yay, finally. Cards. So we're going to go ahead and look at this situation. And basically, we have a standard deck for playing cards. Find the probability that a random card is randomly drawn from the deck is a jack. Okay, red card for so red card, and it has to be randomly drawn from the deck is a jack. So it's like it's got to be red, right? But it's also got to be a jack, or given that it's a jack. So let's see. Again, what is the probability of pulling a red card given that it is a jack? That's basically how I'm reading it. Now, again, the probability of having a jack intersecting with a red is really this. Well, how many jacks are there that are red? And you should realize, well, there's only two red jacks, right? There's the jack of hearts and the jack of diamonds. So in reality, there's only two possible cards out of those 52. But like the formula suggests, probability of drawing a red given that it's a jack, well, we have to consider the probability of getting a jack. Now, remember, intersection of a jack and a red is 2 out of 52 cards, right? But what about the probability of getting a jack? Well, how many jacks are there? There's 4 of them, All right, 4 out of 52. So ultimately, you'll go ahead and get this to cancel out. You can actually multiply both the numerator by 52, and they'll cancel out. You'll get 2 over 4, reduce, always reduce. And that's a 1 out of 2 chance, or 50% chance, that you're going to draw um, a red jack. All right, now given it that it's a jack. So notice how it's like given that it's a jack. Now we really care. Okay, so it's like, yeah, what's the probability of putting red? But it has to be a jack. All right, well, that's where you consider, well, there's 4 jacks total, but only 2 of them are red. So that's really where you're applying the formula. All right, so let's look at another example. Example 2, from a standard deck of playing cards, find the probability that a face card, okay, randomly drawn from the deck is a king. And please note that ace is not a face card. Oh boy, well, let's see. So which event is which? All right, so let's see. What is the probability of us drawing? Let me see if I'm reading this right. Face card is a king. So the probability of drawing a king given that it's a face card. Okay, that's how I'm reading it. So again, this is let's see, face, and that's king. Okay, so notice how I'm taking apart my events to try to make sense of my formula. So the probability of drawing a king, given that it's a face card, has to be, well, the probability of the king intersecting the face card, because it has to be both, right? Because a king is a face card, divided by the probability that it happens to be from a face card. Well, let's consider how many kings are in. So I'm taking care of the numerator, the probability of k intersecting f. Well, how many kings are there? And you should realize there's 4 kings out of, again, 52 cards. But of those kings, we're drawing from face cards. Well, how many face cards are there? We got the jack, we got the queen, we got the king, and there's 4 suits. So what's 4 times 3? That's 12. So we actually have 12 face cards out of our entire deck, which our entire deck is out of 52 again. So 12 out of 52. And we go ahead and cancel out the 52s, right? Common denominators down there. So 4 out of 12, we can reduce. That's 1 over 4. And there we go. Oop, not 1 out of 4. Silly me. 1 out of 3. All right, so there's a 1 out of 3 chance that you're going to basically you're going to get a king if you were to draw from nothing but face cards. All right, and that makes sense because it's like, there's only 12 face cards, and how many are actually going to be kings, and it's going to only be 4 out of those 12. All right, so here's your turn. Standard deck of playing cards. Find the probability that a queen is randomly drawn from the deck is a diamond. All right, so again, consider the probability of drawing a queen. So what you're really doing here is the probability of you drawing a diamond card given that it's a queen. All right, so set up the formula accordingly, and you should get a nice little fraction. There's your homework. Let me know if you have any questions, and good luck. And there's the Joker.